Welcome to this explainer. Let's dive right in. Today, we're dissecting the technical anatomy of confirm. Essentially, this is a deterministic statistical engine specifically designed to measure relationship magnitude. If you work with categorical data and you need strict, quantitative measurements to understand exactly how your variables are interacting, well, you really need to know how this engine works under the hood. So let's jump straight into the math. We've got a very straightforward roadmap for today. We'll start by looking at the statistical engine itself, move into how we measure magnitude, unpack the neutral grading scale, trace the engine's origins in the energy sector, and finally wrap up with offline verification. All right, part one, a statistical engine that goes beyond machine learning. Now, there is a really fascinating contrast here between two totally different analytical approaches. On one hand, you have machine learning, which is incredibly powerful but inherently brings along these opaque internals and, at best, partial explanation. Confirm goes in a completely different direction. It relies entirely on classical statistics. We're talking zero AI components, no neural networks, no hidden layers. Because it leans on established early 20th century mathematics, every single calculation is fully transparent and absolutely reproducible.
The real star of the show here is Cramer's V. This is a very straightforward measurement of magnitude. Think of it kind of like a Pearson correlation coefficient, but it's specifically built for categorical variables. It gives us a strict numerical value right between 0.0 and 1.0. A 0 means complete statistical independence, while a 1 means you've got a perfect mathematical association. It literally tells us exactly how much of a relationship exists between the categories we're looking at.
Moving right along to part two, measuring relationship magnitude and mapping out the computation path.
The engine follows an exact three-step deterministic pathway. You go from raw categorical inputs straight to an effect size with absolutely zero detours. Step 1, you submit your categorical decisions alongside their corresponding group labels. Step 2, the engine takes that, constructs a contingency table, and runs a Pearson chi-square test of independence. And then step 3, it computes the Cramer's V statistic to actually measure the effect size. It's a highly direct, purely mathematical pipeline.
It's really important to notice how the engine cleanly separates its mathematical tasks. It uses the chi-square test for one specific reason, to identify the presence of a statistical link. It's basically asking, hey, is there a mathematically significant pattern here, or are we just looking at random noise? Once that significance is locked in, Cramer's V steps up to strictly measure its absolute magnitude. So one tells you if the relationship is mathematically real, and the other tells you exactly how large it is. Which brings us to part 3. The neutral grading scale and its tiers of effect size. Okay, let's break down these A through F tiers. Now, this is absolutely crucial. These are strictly neutral quantitative effect size brackets. They are anchored directly to published meta-analytic benchmarks. So a Cramer's V of 0.30 or higher drops into the A tier, which denotes a strong statistical effect. A value below 0.05 results in an F. You have to understand that these tiers are entirely separate from performance evaluation. They aren't qualitative scores, they simply categorize the sheer mathematical strength of the association. I really want to hammer this point home. These letter grades are purely quantitative measurements. If you receive an A, it just means the engine measured a large statistical effect between your categories. If you get an F, the engine is literally just reporting that there's no mathematically detectable relationship present in that data. The tool provides a completely neutral diagnostic reading. Any operational decisions or judgments are left entirely up to the human reviewer.
I love this quote because it hits the nail on the head. Think of the engine as an absolute value. It measures the magnitude of variation without assigning any evaluative judgment whatsoever. High variation? Well, maybe that's exactly what you expect in your data, or maybe it's something you need to investigate. The engine doesn't make that call for you. It strictly tells you how much variation mathematically exists across your categories, handing you a precise, objective measurement to work with.
Let's pivot to part 4 and look at where this came from: energy sector origins and scaling the mathematics. You might be surprised to learn that international energy operators actually apply this exact math to categorize rock formations and forecast physical variables. This engine was originally built to solve some incredibly complex geophysical requirements. Operators needed a foolproof way to guarantee that their categorical classifications, like identifying sandstone versus shale, were mathematically consistent across different geological formations. They used this exact same chi-square and Cramer's V framework to check forecast patterns by well type and to validate seismic interpretations across massive surveys.
The physics domain is unforgiving, right? It demanded a purely mathematical measurement of categorical variables, stripping away all human subjective interpretation. When an international energy operator is making high-stakes, multi-million-dollar drilling decisions based on categorical data, they absolutely cannot rely on averages alone. They require a rigorous, independent measurement that confirms the statistical consistency of the data before any operational deployment. That intense physical requirement is exactly what forged the strict, deterministic architecture of this engine.
And finally, Part 5. Offline verification and proofs, and what this looks like in deployment reality.
This is a massive operational detail. The engine is 100% offline. In highly regulated environments where data privacy is the top priority, this is a critical structural feature. The engine functions entirely on your local machine. It doesn't transmit data, it doesn't hook into cloud computing, and it requires literally 0 network calls to execute its statistical tests. Your categorical data never leaves your secure environment.
Because the engine is built on classical statistics rather than opaque algorithms, it generates what we call a self-verifying mathematical proof artifact. This means every single calculation it performs can be manually reproduced by hand. You aren't just handed a final number in a black box, you get the entire mathematical receipt. It shows you the observed tables, the expected frequencies, and the exact step-by-step math it used to arrive at that final Cramer's VFX size.
This verifiable manifest guarantees the strict reproducibility of the measured statistical association's strength. Every single decision the engine makes during intake is logged in a JSON manifest. The system actually takes the time to recompute the intermediate quantities from the observed table just to mathematically assert that the numbers align perfectly. This printed proof ensures that the deterministic output can never drift, giving you a rock-solid audit trail that you can hand straight to a compliance team or a statistician.
We'll leave you with this thought to wrap up the explainer today. Think about it. If your categorical models are evaluated solely on average output, what hidden relationship magnitudes are currently operating completely undetected inside your categorical data? The technical anatomy we've explored today proves that measuring the exact mathematical strength of these categorical associations is not only possible, but it's highly accessible through reproducible classical statistics. Thanks for joining me to explore the deterministic architecture of Confirm.